Hey, we're live. Good to see myself streaming again. We're gonna do even more lead code, need code type of questions. I'm doing this currently to prepare for FANG interviews. Once I master all of those need code problems, then I will check out other competitive programming stuff, like CSS. I heard that CSS is very good at coder, and but after CSS, I will probably do uh, Code Forces, the Russian one. Yeah, Code Forces. Yeah, that's it. That's it. Um, Graphs, bit manipulation. Just review some of the things that we did in a previous chapter. We did single number of 1 bits, counting bits. Code was like, yeah, with counting bits. All right, with single number, um, array of nums. Every element appears twice except for one. Find that single one. You must implement a solution with a linear runtime complexity twice. So thing about this is that, if like 5 as a bitwise thing, as a bitwise operation and not Boolean operation, will give me a 0 essentially, because XOR operations cancels out similar bits. If it is 1 and 1, they're gonna be 0. If it is 0 and 0, they're gonna be 0. Uh, so these are gonna cancel out as bits. These are gonna cancel out. So if we do 5 XOR 5 XOR 3, this is gonna be same as 0. We know that this is 0, 0 XOR 3, and 0 XOR 3 will be just 3. Now, why would that be? XORing with 0 would essentially give the same number, because 0 XOR 0, 0 XOR 0 is gonna be 0 obviously, and 1 XOR 0 is gonna be 1. So the bit pattern of this is not gonna change because this is just 0. Another thing is that with XOR operation, with XOR operation, we can change the order of those numbers. Like, all right, we get that 5 XOR 5 is 0, but is uh, 5. But if we switched the ordering of those numbers, let's say 5 is here and 3 is here, do we still get the same thing? Because, right, like 5 XOR 3 is gonna be something, some bit pattern, and this some bit pattern XOR with 5 could be like anything. Like, why does it have to be 3? And the thing is, we use two characteristics of XOR operation. One is that this is same as this. So the ordering of the XOR operation does not matter. Do we XOR this first or do we XOR this first? It does not matter. And the second is that we can change. Second trait of XOR is that if we have A XOR B, this is gonna be same as B XOR A. Well, I think this can be proved in discrete mathematics. Both of this stuff can be proved very easily with just truth tables. If you're gonna draw a truth table for A XOR B and B XOR A, it's gonna be essentially the same thing. And I think the similar goes for parentheses. It can also be proved with truth tables, probably. But yeah, this is why this solution works. I think coming up with this algorithm is very simple. We just get a result and keep XORing whatever elements are here in this vector. But why is it working? Yeah, I just discussed why it works here. So submit this again, so we save this solution, this explanation. Okay, then we discussed this problem. Numbers or number of 1 bits given a positive integer and write a function that returns the number of set bits. Set bit means 1 in its binary expression, also known as Hamming weight. So Hamming weight is number of ones in a binary number, I guess, but it can also mean like Hamming weight. Every number has a Hamming weight, even in decimal systems. And Hamming weight is simply the number of non-zero digits. So in the case of 11, number of non-zero digits is 2 because we have 1 and 1. In other binary, like here, Hamming weight would be 3 because there is 3 ones. Now, how did we solve this problem? I think there was other previous submissions. No, it's only one. Okay. The thing with this is that the weight, we initialize the weight variable, which we are later going to return, increment step by step, and return. We have a for loop iterating over 1 to 32 essentially, iterating over 32 times. Now, why is that? Why would that be? Or 31 times? How many times is this gonna execute? This is gonna execute 0 to 30, which means 31 times. But we use this for loop. So the int in C++ is a 32, so this int is a 32-bit int. So we essentially check 32 times. Check 32 times how many. So we have to like check each digit in this int. For checking that, we generate a bit mask, which is gonna be a 1. 1 in binary is a lot of zeros and then 1 in the end. And if we shift this with 0, it's gonna be nothing. But if we shift this binary number to with 1 to the left, it's gonna be 1 0. So this 1 is gonna get put here and put to the left of itself, and its old place is gonna be filled with 0. So like this is what shifting means. This is shifting. So this 1 shifts left. All right, we generate this bit mask, and we can end inside of C++, if any non-zero value is false, is true. So when we end this bit mask and some number, obviously all of these bits are gonna be set to 0 because 0 and something is gonna be 0. But like 1 and the digit, so to say, above this number is gonna be whatever it was. So 0 and x, all right, I'll just write this down. 0 and x is gonna be 0, but 1 and x is gonna be x. So when we shift, like for example, 3 times, we are like with this operation, we essentially understand if this bit, like if the third bit is 1 or 0. If it is 0, we do not add to the Hamming weight. This is gonna be false, and we do not add to the Hamming weight. If it is non-zero, like any other value, literally, it can be 1, 2, 3, whatever, it will add to the Hamming weight. So I'll also give you another example. Let's say we have some number like 1, 0, 1, 0, and then we have a bit mask. How do we check if this number is, like what bit is this number? All right, we generate this bit mask, and then we end. And then we end. So this is gonna generate 0, 0, 0, 0. If this whole thing is 0, the bit, if whole thing is 0, 0, then the bit was also 0. If all right, let's do this same number but different bit mask. 0, 1, 0, 0, 1, 0, and we do the end operation here. It's gonna be 0, 0, 1, 0. If whole thing is non-zero, the bit was 1. This is how it works. This generates the whole thing, and the whole thing, if it is non-zero, the ith from the left ith element was non-zero or was 0, and then all right, this is a very easy logic. We can keep explaining this forever, but bit mask. Okay, counting bits. Now this is a little bit different problem. Submissions. I think other worked. No. Did this submission also work? No. Okay. So let's describe the problem. Counting bits. Given an integer n, return an array n's. Array n's. It should be n's of length n plus 1, such that for each I n, n's I is the number of ones of the binary representations of I. So this essentially asks for a Hamming weight. Number of ones is obviously a Hamming weight. So we have this count bits from numbers. For numbers 0 to n, we have to find out a Hamming weight of that number. For 0, this is 0. For 1, it's gonna be 1, obviously. For 2, it's gonna be 1 because the binary pattern, the binary bit pattern is 1 and 0. Binary representations of ith number, blank. So what we do here is we obviously start from, we initialize this vector. I think this fills the elements with zeros. We iterate from 1 including n all the way up including to n, up to including n. Int num is gonna be I. We have our number, we have our count. Obviously we're gonna count into this variable, while num equals to num and num minus 1. We increase the count, and we do the same thing if the num is not 0 or while not 0. Once the num is reduced to 0, we update the result vector. So this works. Basically, this is a way of counting Hamming weight. But why? Why does it work? It works because bitwise ending with previous integer causes the last set bit, to turn 0. So question becomes, how many of those set bits do you turn to 0 unless all of them are 0? So ending with the previous, like that's an interesting thing. You have some bit pattern, and then you end it with a previous number. That's it. If you end it with a previous number, this is just gonna be 0. What you get is the same bit pattern, but the last one, the rightmost one, is gonna be just 0. That's it. Like, this is how it works for all numbers. Even if you have all like ones, and like the -1 is gonna be like this, it just makes it makes the rightmost set bit 1. Now I have another question, and the question is, what if we have something like this, a power of 2? The previous number is simply gonna be this. So we end it, and all of this is 0, and this also becomes 0 because this is 0. So we are done with this. Now, when we have a power of 2 and we end with the previous number, we can only do this operation for 1 because there is only one single bit to turn 0. So the count is only gonna be incremented 1 time, which is gonna give us a result, which is gonna give us a count of 1. Now another problem. this was it. Um, this problem can also be solved dynamically. And in this solution, you essentially build up a vector. And as you are iterating over the numbers from 1 to n, you are building up that vector. So you start by building a dp vector of size n plus 1. Why n plus 1? Because you want the last element of the vector to have index n, and the first one to have index 0, but 0's bit pattern is obviously going to be 0, and it is just set to 0 all the way you calculate an offset while iterating. Now, what is this offset? This offset is simply going to be a most recent previous power of 2. You see the offset starts as 1, and you only update it when offset times 2 becomes something. So the offset is just going to be multiplied by 2. Offset is just a multiples of 2. No, at index 1, the previous most recent power of 2 was obviously 1, because 1 is 2 power to 0. 2 power to the 0. So when you reach another number that is multiple of 2, that is power of 2 actually, you're gonna update the offset. Now, why do we need this? We need this because how can I say that? Let's just do it here. This solution, dp explanation. Now you have some number, right? And right, you have some number, and like you want to know how many. You have a question, how many set bits, and the answer is as many as whatever this number had plus 1. Plus 1 obviously, because this is 1. This is 1. As many as this plus 1. Now, how do you calculate this number? Whatever this was, plus 1. We're here, right? So how do you get whatever this is? You get whatever this is by current number minus last recent multiple of 2 or the offset because offset is gonna be 1 in the first and zeros in the back. So when you subtract this to this, you're gonna get this, and you already know the answer of this. This is how we dynamically build up our solution. Now there is another question. We start with let's say index 0, 1, 2, 3, 4, 5, 6, 7, and we are gonna get the answers. The ans vector that is the result of our solution. We start with 0. Now when you are at the 1, the offset is 1. So you go like, alright, index 1 minus offset 1, which is index 0. Index 0's answer was 1, so we add 1. Now you go to 2, and offset times 2 is 2, another multiple of 2 discovered, and offset has updated. Offset has updated to 0, so our index minus offset is now gonna be here at 0. So in a way you start counting from 0, you know. You go to 0, 0's weight was 0's answer was 0, and then you add just 1 to it. Now 3. At 3 offset, at index 3, the offset is still 2. So index minus offset is gonna take you to 1. 1's bit pattern was 1. 1's Hamming weight was 1. So we have to add 1 to it. 0. And this is basically how, alright, index 4, new offset. Offset is now 4. What is the answer of 4? You go to index minus offset, you take that answer, and then you add 1 to it. Same with 5. Index offset is still 4. You go to 1. You go to 5 minus 4, 1. Answer to 1 is 1. You add 1 to it is 2. Same thing with 6. 6 is not a multiple of 2. It's not a power of 2, so we do not update it. Here the offset is still 4. 6 minus 4 is 2. 2's answer is 1. 1 plus 1 is 2. 8, similar thing. A bit pattern, index minus offset in this case is gonna be 3. Right? 7 minus 4 is 3. 3's answer is 2, and 7's answer is gonna be 3. This like very beautifully builds up the DP array, which is essentially a result for our problem. I think this is a very beautiful, this is definitely not intuitive for a beginner. Like when you're a beginner, this is not intuitive. I don't think you can build up this easily. At least I couldn't have. But once you realize how it works and why it works, and you sort of pose questions and give it answers, It's a really beautiful algorithm. Should we just code this solution up just for fun? Let's go. So the ans, whoa, ans, we start iterating int I from 0 all the way to n, I plus plus. We start doing that. We have a DP. We need an offset here already. Offset is gonna be 1. Why did I write this 0 when I said it should be 1? Offset is 1. So we see if offset times 2 equal to I. So if new power of 2 was discovered, offset becomes that. And the count, do we have a count variable? Equals, no, we don't have a count variable. dp I is gonna be equal to 1 plus whatever I minus offset is. And this should be it. Like, this should really be it. DP. That's what happens when you learn a solution from a write-up. You just... Did it work? Yes. Ooh, that was good. Till now, I overviewed the problems of previous day, which took 30 minutes. So this was just a warm-up. Let me check out the stream. Let me check out the stream. What, upcoming? Whoa. Why is it not streaming? Morning session. Oh, this one is streaming. Upcoming? Damn. How do I delete this? Ah, I suck at this. I suck at YouTubing. So here you kind of see what kind of projects I dabble with. I dabbled with building with TCP IP stack and pussied out the first time I occurred a C error. I pussied out because I downloaded the project which was already built. I tried to compile it and it wouldn't because there is some error, and I got scared of diving into the fixing the error because what the hell, it's other person's C code. I can't do that can't do that fast, but so I kind of gave up on that. 2 days ago I also did Golang by example, and then I pussied out because I kind of did not understand closures. No, actually, I think I understand closures. It's not a hard problem, but I pussied out because we went through that Golang by example website, and the thing was, all right, what is the reason? Like, why are we doing this closure things? Why are we doing this weird function? What is the point? So then I did what's it called? Closures, periodic functions, or what? Golang by example. It was go by example, sorry. Go by example. I think I was coroutines. No, I did not. Range over built-in types, pointers, strings, and runes, structs, methods, interfaces, nouns, generics, custom errors, coroutines, channels. I was at closures. Yeah. So a function that returns another function, which we defined anonymously in the body of insec, the return function closes over the variable I to form a closure. This is the sentence that I did not really understand. And so like this function, because this is defined in the scope of this function, like this function has access to this. And when you initialize a new function, xint, this is the function which is a bit odd to see. Like you are declaring a function like a variable. Here are no parentheses, but here are parentheses, because parentheses means to call a function. So you declare a function and then you call it with parentheses. And what's going to happen is that every time you call this function, it's going to have access to its own I. And it also increments I. So you're going to get 1, 2, 3, because you call it 3 times, and then you declare a new function, which is, you see, this is a bad example because the namings are so similar. It's like you are reassigning to the same variable, which is really not the case. You're just creating a new function, not the, like this and this are two totally different things. Like they are different functions. But you assign the same thing, and now this is gonna start from 0. So it's gonna add 1 to 0 and then return that number. Closure. Anonymous functions which can form closures. Anonymous functions are useful when you want to declare a function inline without having to name it. So anonymous functions form closures, closes over this variable. Closes over this variable. We call int sec, assigning the result to a function to a next int. All right, this is not a Golang video. We are doing a Leetcode session here, not a Golang session, but now I understand what they meant. So basically, why would this kind of functions be used? Why would closures and anonymous inline functions be used? Sometimes you want to call a function, but you also want to do another thing every time you call that function. So for example, we saw an example of middleware, like a web server middleware. Every time, let's say we hit login function, we also, let's say that we also want to count how many times the login function was hit. This is how we do it, essentially. So this would be a login function, like a normal login function, and this would be a, how do you say, a closure. So this would be a count of how many times the user logged in, which you increment here. And it said that basically this is how middleware works. In Golang, at least. Yeah, non-generics, defer. Like what's generics in Golang? Because in C++ generic is a like an interesting thing. Let's say you have a vector of ints. Let's say you have a function that handles ints. You also want to have a function that handles doubles and floats. That's generics in C++. You have a vector of ints, you also have a vector of floats. Generics. Go has added support for generics type parameters. Oh, this is a nasty example. So much text here. As an example of a generic function, slices index called as an example of a generic function, slices index takes a slice of any comparable type. Slice of any comparable type. Any comparable type. Any comparable type and an element of that type. So this is a slice. And this is element comparable. The comparable constraint means that we can compare values of this type with, obviously, for more thorough explanations of this type signature, see this. Okay, we don't care. Note that this function exists only in standard library, exists in the standard library as slices index. So yeah, so we're basically re-implementing slices index function. Now what's that? Now what is that? I'm gonna ask ChatGPT. I'm gonna do the heresy and I'm gonna ask ChatGPT. What is? Where is that thing? Where is that thing? What the hell is this? Is a type parameter constraint syntax in Go generics. Here is a breakdown. S is a type parameter. E is another type parameter constrained by comparable. No, this is just a parameter. I think this can be called anything. As a type parameter, E is another type parameter constrained by comparable. Yeah, like here we say that it has to be comparable, so it is basically slice of this means any type with underlying type slice E. This means S can be any type whose underlying type is a slice of E. So why do we need this? Why can't just any type slice of E? Why this? Like, why do we need what does it mean? What or say? Why do we need this? Means has underlying type in Go generics. Has underlying type. So this has underlying type. What's underlying type? It's basically any. Without tilde. Is this tilde? SE would mean exactly the type E, so only row slices would work. With this, it means allow any type whose underlying type is a slice E, including name parameters. Type int, its underlying type is .int. Oh, my ints slash int underlying type. My int wouldn't be allowed. Wow. Ah, okay. So in Go, you can basically name types, like you can have type my int and then int. And then this underlying type would not be wouldn't be allowed. I think I get that. Now we understand this, but we have to see it somewhere in the real code. You know, that's why building project is important. Is that you see it in real life. Like somebody came up with this feature in Golang, and this is a like a very delicate feature, right? Like a very specific rule that we have types, and in a function signature you can not allow underlying types, or you can allow underlying types. But why do we need to not allow, or why do we need to specifically allow? This is, I think, a historical problem, like a problem that has a historical background. Like somebody had a really good reason to add this sign, essentially. But we don't know that reason yet. We know it works, but we don't know why it works. Alright, you can have basically a generics E this is a generic declaration SS and VE. V is gonna be S is a slice, and V is just an element in it. So you iterate over slice. If it equals to V, or this element, it returns I. Yikes. Let's go back to Leetcode, bro. This is a Leetcode session, not a Golang session. What are you doing? Reverse bits. I know what this problem is gonna do. I know it. Reverse a bit of given 32 bits unsigned integer. So in C++, when you see this ugly looking variable types, it is just unsigned integer 32 bits. That's what it means. And what does the T mean here? Unsigned integer 32T. Alright. In CPP, what does T mean? Suffix stands for type. It's just a naming convention. Unsigned 32 integer type stands for type. All right. But note that in some languages, such as Java, there is no unsigned integer type. In this case, both input and output will be given as a signed integer type. They should not affect your implementation, as integers internal binary representation is the same, whether it is signed or unsigned. As a signed integer type. In Java, compiler represents the signed integers using 2's complement notation. There, for example, 2 above or below, really, represents the signed integer. Signed integer 2, 3, minus 3. And the output represents whatever. So whatever bit pattern you are given, you should just reverse the bit pattern, nothing else. So here we have a lot of ones and then 0, 1. Here we have 1, 0 and then a lot of i's. But those i's are obviously also reversed. The input binary string represents the unsigned integer, so return, which is a binary representation, Okay. Bit. No, I don't know how to do this. I have zero idea, actually. There is a little sub problem. How do we, let's say we have another int. Let's call it A. We want to copy the values of n bit by bit to A. How do we do this? What we can do, what we can hope to achieve is that we can do the same shifting operation. Like we're gonna declare 1, 1 and shift it, say, 3 times. Or we're gonna declare 1. Yeah, essentially like start shifting it 30 times. 31 times. Or it's gonna be shifted to 31 times. Yeah, at max. And we're gonna know the what bit was that? Was it 1 or was it 0? Okay, we're gonna know that. So if that bit that bit, for what we're doing, we're iterating over the bit pattern of n from right to left, or from right to left. And that bit has to be somehow appended to the, how do you say, should like append it to A. How do we do that? All right, let's just write a for loop that does this for int 0. It's not gonna shift at all. Int bit mask is gonna be one shifted I times. Just for compilation purposes, and let's see out bit mask. All right, this is good. This is good. 1 2 to 120 . Bit mask. Now, how do we? All right, we can get so n int is 0 int bit. Is this bit and bit mask? If this is 0, if bit equals 0, it was 0. If non-zero, actual bit was 1. Bit was 1. Now we have to write this. So if bit append 1, or else, so if not bit append 0. How do we append? Like now the problem is appending. How do we append? We don't need this anymore. Just keeps the code ugly. Bit mask. How do we append this bit? How do we append 1 to A? I have a great idea. I think I have a great idea. A is gonna be equal to ORing up. We have to be careful here. ORing to a new bit mask. New bit mask is gonna be 128 shifted right I times. No, 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 no. Not right. That's not right because oh shoot, this is actually right. This is right. Um, so ORing with 0, like X or 0. Oh no, that's a bad pattern. A or 0 is just whatever A was. And 1 or A or A or 1 is gonna be 1, no matter what. Uh, so this bit mask is gonna keep the previous like left and right elements digits the same, but it's gonna make the ith element 1. Else we have to make that 0, else we don't do anything. Like it's already 0, so we don't do anything. So return A. This should work. Wrong answer. Expected was. Oh, we're not even. Damn, we're not even right. There is something very wrong because the bit patterns aren't even similar. Anyhow, they should be similar. If bit, let's just see out 1. See out 1. Yeah, let's just do that. And if not, let's just see out 0. Let's run. Now we should compare this to this. 0, 0, 1, 1, 1. 0, 0, 1, 0, 0, 0. Then we have 5 zeros. Then we have 1. Then we have 0. Then we have 1. Then we have 2 zeros. Then we have 1, 0, 1, and 6 zeros. So we printed correct. So my intuition is right, but this appending thing is not it's not working correctly. Oh, this is bad. This should not be 128. What is 1 powered to the 30? Oh. Battery is gone. 2 POV 31. CPP. Powers and CPP. The POV function is used to calculate. So it is part of the CMath header file POV base and exponent. So POV POV 2 to the 30. Shifted binary expression. Oh, what is this? Invalid operations to binary expression, aka double and int. Just int this. Outside of range of values of int. Oh. My bad. Ah, voila, it works. It works. Now, this solution is probably slow because of this. We have A, but we should also have a power uint 32t. What should we name this? We should name this. What is it really? Like leftmost 1 bit? What is it called? Let's just call it 1. 1 shifted. It's just 1. Like 1. This 1. Submit. This should be faster. It's just a little bit faster. Just a little bit faster. Oh, and now it beats 100%. Okay, whatever. Let's just see what the solution had to say, by the way. Did it say anything new? So people that say that you shouldn't look at solutions are wrong, because you should look at solutions even if you solve the problem, because maybe there was something similar. See? Now that's a new type of thing. Brute force, binary. If binary ended with these. Oh, it just creates a string. I think we did the brute force solution. Did we? Append to, yeah, we did this. So turns out we only did this in a brute force fashion. Time complexity 1, space complexity 1, a bit manipulation. So he iterates over 32 bits. This is good. Bit equals n. He shifted this stuff I times to the right, and then ended with one. So this gets the last bit, and then he just appended that bit to like this. All right, this is good. This is good. blah, blah, blah. Here we used a bit mask to get the last numbers. Here he kind of does the same thing. It's all the same thing, really, just a bit manipulation in different forms. Bit, then it shifts this bit towards this. And then now, this is what an important thing is. He adds. Since the result is 0, adding. Does that make sense? Does that make sense? Yeah, obviously it does make sense because the bit is just zeros and only one set bit. And yeah, I think it makes sense. Now this is uint. Bit manipulation optimal. Wow, this is even better. We have a return value n, same as n. We shifted. What's that? He shifted right 16 times and then shifted left 16 times. And then ORed it. And that's a new ret. Now he ended. What is this? F's are just going to be F's are gonna be ones. Now this number is F is 16, right? Now F is actually 15 because we have 1 to 9, then we have 10 as A, B, C, D, E, F, which means 10, 11, 12, 13, 14, 15. So F is 15. To write 15 as a binary number, you need how many digits? 1, 2, 4, 8. You need 4 digits. So this one number represents really 4 digits. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 by 4 is 32. So this just represents a bit pattern of a uint type, probably. So this is just a bit pattern. Now what he does here is that he ends this and shifts right to the 8. Now why would he do that? So we have a 32 uint. First 8 bits are set to 1, next 8 bits are set to 0, next 8 bits are 1s, zeros. And then he shifted right by 8. Oh damn, god damn, this is fucking hard. This is fucking hard. Or what's A's? You see, I wonder what the solution is, what the explanation is, but this is taking too much time. So I don't care for the optimal. Missing number. sum of two integers, reverse integer, missing number. Let's do missing number. But I'm getting tired because I have been talking for 1 and 15 hours. Well, I think I should just take a 5-minute break and I'll come back. So I'm back. We have 30 minutes to get my laundry. So, given an array nums containing n distinct numbers from range, return only number in the range that is missing from the array. Wow, that's very interesting. Missing from the array nums. We have nums, and it is supposed to cover from 0 to n. We have to find that number. That number. Array nums. N plus 1. Explanation. Since there are 3 numbers, so all numbers are in range 2 is missing in the number since. Does not appear. Does not appear. We will need this n. Honestly, I have no idea. What if we end all the I have no idea. Absolutely zero idea. Time complexity. Well, sum. We sum up all numbers. Oh, this is so easy. This is so easy. This is a mathematical solution, though. It's not a bit pattern solution. Some trick. Sum equals to 0, I equals to 1. Total, there is num size. Nums size. So 0 to n. If we have n size, 0 to n minus 1, right? So total will be summed by ice. Ice, right? total would be summed by I. And sum would be summed by nums.ice. Now, why would the difference give us the 2? Expected total would be 3, 0, 1, 2. Sum right. What's the bit thing then? Like, what's up with bits? Wow, this is sponsored by GitLab. AI in your dev process, it's time. Okay, it's time to accelerate. Brute force. Has set bitwise XOR. When two identical numbers, so using this property, we can efficiently find the missing number. How we can missing number? Okay. I understand that. I understand it now. That's it. So n, right? The last, like the biggest number would be n here. It contains numbers n to n. Like the last number or the biggest number would be n2 in the array. But one number is gonna be missing. Now, can n itself be missing? I have that question. Um, why not? I guess, but whatever. Da, 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 da. And size, num size. Ooh, damn. Start with. We also need an index, man. We also need an index. Now total will be XORed, like literally every element, I to n. I to n. Like literally 0 to n. It will be XORed. But the result will be XORed only the values. So this will have some numbers, this will have some numbers, and once we XOR two of them, we will be left with is that it? Is that it? Wow. This is a trick solution, really. So Actual result will have XORed, like the literal numbers, and the total will have the actual numbers, but also another number. Another extra number. And we XOR this stuff. XOR result. We XOR this stuff also. And then when we XOR it out, two of them again, the missing part, all the others stuff is gonna cancel each other out, while the missing stuff will remain. This is a pretty decent solution, but I also saw, like, let's do the mathematical solution, not the XOR solution. Let's just actually sum things up. Numbers, result, total. I think we can just use add instead of XOR, and minus instead of. Does it also work? Haha, that's so cool. That is so cool. It got submitted. Got submitted. It worked. So what happens is that you're just gonna sum every number from 0, including I, in total. And then I'm just gonna, in result, I'm just gonna sum the actual numbers in the vector. But this will have a, like, this will miss one number from 0 to n. This will miss one number from 0 to n. And when we subtract, we're gonna get the missing number. Let's say the example. Total is gonna be, so the total will have sums of, let's say the actual example, that's 3. So this is an array, this is a vector of size 3, then it should have, so the total would be 0 plus 1, 0 plus 1 plus 2 plus 3. But the actual result is gonna be is like 3 plus 0 plus 1. Now, total minus res equals missing, or missing equals. This is how it works. So, yeah, pretty good problem. Sum of two integers. I think I have 10 more minutes, so let's just go through this. Sum of two integers. Given two integers, then the sum of two integers without using the operators plus and minus. I think one of my lecturers gave me this problem in a lecture, and I kind of fumbled. I went through a binary explanation, like a binary summation algorithm. So this is a medium actually. Seen this question in real life before. 1.5, yes. course I know. Thank you for feedback. Accepted topics, math, bit manipulation. So 0, 0, 0, 0, 1 and 0, 0. The numbers aren't really big. The numbers are not really big. I wonder if I just return A or B, A or B. Isn't this solution? No. No, ORing is not enough. Because if you OR 1 by 1, you're just gonna get 1 again. ORing is not enough. I think you also need a carry values. How is it solved? Let me just check out the write-up, man. I don't have time for this. I gotta leave, but I'm curious about the solution. Oh wow, this is a great solution. This is a great solution. So bit manipulation, get some carry. Optimal mask, carry current bit, carry bit. Wow, this is not good. You're using that operation. A bit plus B bit plus carry. This is not good, man. This is not good. Boolean AND. You must, I think he has to use a Boolean AND or something. Boolean OR maybe. Bit manipulation. Alright, this is a solution that I'm working for, that I'm aiming for. While B, whoa, oh, I get it. So, what is he doing? Carry. We have some bits. Let's say 0, 1, 0, 1, 0, 1, and we have 1, 1, 0. Let's follow this instruction. This is A and this is B. In carry is just gonna be A and B shifted left to 1. Which is a very weird way of looking at things. A and B shifted by 1. He actually XORs A with B. Now, what does this do? This does a very good thing, that adding B equals carry. This is a really cool algorithm. mask? Why do you need this mask for? What do you need this mask for? What do you need this mask for? Carry. Um, we get a carry value by XORing by ending 1. But then why do we shift it? So just doing this, um, so where we are um, adding two bits in a binary number, and we have bit A and bit B, and we need to calculate the result. We have 2 digits in the result. One is a carry digit and another is just a sum. So sum can be calculated using XOR, and carry can be calculated by ending and A and B, because we only have a carry bit if both A and B are true. If both A and B are ones, so to say, this is why carrying is done by A and B and then shifting it left. Shifting means carrying, and this is just calculating it. Carry, XORing. But doing this once is obviously not enough, because carry operation is just gonna change the next add cycle. Oh, damn, I don't really get this one. I don't really know how to explain this, but I know that it will work. Time is 2. All right, I have to go now. I have to go very soon. And let's just work my way through an example, and then I will go. Then I will go. Then I will go. We have 2 and 3. Right, 2 is 1 and 0. and 3 is 1 and 1. And A is gonna be this. We calculate carries, which is gonna be, here it's gonna be like 0 carries with and it's gonna be and we do this. We have to do this. Now this carries this. A is gonna become A XOR B. This will make it 0 and 0 and 1. And then B is gonna become carry. So this is gonna be this one. B. A new carry is gonna be calculated, which is going to be calculated by ending. So 0, 0, 0, which is gonna be zeros, and a 0 also. So new carries are gonna be 0, and then this will be assigned to B in the next, and then it will not happen anymore. And then we A XOR B, which is going to be this 5. Now this is 1, 2, 4. Oh, this is 5. All right, this works, but why it works, just don't ask me. This is just great. This is the most Java thing. Get some, like object get some, and then return A plus B. I'm really interested about the solution. Can we play? No, we can't play a video here. All right, stop. No, stop.